Right now you are falling, not through air or water, but through a hole in the fabric of reality itself. A void 2 billion light-years wide stretches beneath you, around you, through you. Every atom of your body, every thought in your mind, every memory you have ever held dear is plunging through an emptiness so vast that light itself takes 2 billion years to cross it. Scientists confirmed this in 2007. They called it the cold spot. They found it by accident while mapping the oldest light in existence. And most people have no idea that this cosmic abyss exists, that it might be a wound in space-time, a fingerprint left by something pressing against our universe from the outside. Something that should not exist. Something that suggests our entire cosmos, every galaxy, every star, every planet, every life form that has ever drawn breath, might be trapped inside a structure so incomprehensibly large that calling it a universe would be like calling the Pacific Ocean a puddle. If you are ready to see reality differently, to question everything you thought you knew about where we are, what we are, and whether existence itself has boundaries, then prepare yourself. We begin. For as long as humans have gazed upward at the night sky, we have believed in limits. The ancient Greeks thought the stars were holes in a celestial sphere, pinpricks of divine light shining through from heaven beyond. Medieval astronomers mapped the cosmos as a series of nested crystal shells rotating around our precious Earth. Even as our understanding expanded, as Copernicus moved us from the center and Galileo showed us moons orbiting other worlds, we clung to the notion that somewhere out there, reality had an edge, a boundary, a place where everything simply stopped. But in 1929, everything we thought we knew began to unravel. Edwin Hubble, working with the 100-inch telescope at Mount Wilson Observatory, discovered something that would haunt cosmologists for nearly a century. The galaxies were running away from us, all of them, in every direction. The farther they were, the faster they fled. The universe was not static, not eternal, not bounded by some crystalline sphere at the edge of creation. It was expanding, growing, stretching like the surface of a balloon being inflated by an invisible breath. This discovery should have answered our oldest question. If the universe is expanding, then it must have been smaller in the past. Run the clock backward far enough, and you arrive at a moment when everything was compressed into a single point of infinite density. The Big Bang, the beginning of space, the beginning of time, the beginning of everything. For decades, this was the story we told ourselves. The universe began, it expanded, and it would continue expanding forever, or perhaps collapse back upon itself in a final cosmic crunch. Either way, the cosmos was a closed system, complete, self-contained. There was nothing outside because outside had no meaning when space itself was the universe. But here is where our comfortable certainty began to crack. In the 1980s, a young physicist named Alan Guth proposed a radical modification to the Big Bang theory. He called it cosmic inflation. In the first unimaginably tiny fraction of a second after the universe began, space did not merely expand. It exploded. It doubled in size, then doubled again, then doubled again, repeating this process so rapidly that regions of space that had been in contact with each other were suddenly separated by distances so vast that light could never bridge the gap between them. The observable universe, everything we can see with our most powerful telescopes, became just a tiny bubble within a much larger inflationary space. This was strange enough, but the mathematics of inflation contained an even more disturbing implication. Once inflation begins, it never completely stops. While our region of space settled down, cooled, formed galaxies and stars, and eventually us, other regions kept inflating. They spawned their own bubble universes. Those bubbles spawned more bubbles. The process continues eternally, creating an infinite foam of cosmos upon cosmos upon cosmos, each one potentially governed by different physical laws, each one containing its own version of reality. We will explore the evidence that suggests our universe is not alone. We will discover the cosmic anomalies that point towards something pressing against us from beyond. And we will reveal what scientists now believe might exist outside the boundaries of everything we have ever known. Prepare yourself. We begin our descent into the unknown. The year was 2004. NASA's Wilkinson Microwave Anisotropy Probe, known to scientists as WMAP, had been orbiting a point in space 1,000,000 miles from Earth, patiently collecting the oldest light in existence. This light, the cosmic microwave background radiation, had been traveling for 13.8 billion years. It was released when the universe was just 380,000 years old, when the primordial plasma finally cooled enough for atoms to form and light to escape. It was, in essence, a baby picture of reality. A snapshot of the cosmos before galaxies existed, before stars ignited, before matter had organized itself into anything more complex than a faint fog of hydrogen and helium. Scientists expected this ancient light to tell a simple story. The Big Bang model, refined over decades, made specific predictions about how the cosmic microwave background should appear. It should be almost perfectly uniform, a gentle bath of radiation filling all of space with the same temperature. Almost uniform, but not quite. Tiny fluctuations, variations of just 1 part in 100,000, should mark the seeds of future cosmic structures. Regions slightly denser than average would eventually collapse under their own gravity, forming the galaxies we see today. And for the most part, the WMAP data confirmed these predictions beautifully. The universe was 13.8 billion years old. It was geometrically flat. It was composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The fluctuations in the cosmic microwave background matched theoretical expectations with extraordinary precision, but hidden in the data was an anomaly that no one could explain. In the southern sky, toward the constellation Eridanus, the cosmic microwave background contained a region that was simply too cold, not by much. The temperature difference was measured in millionths of a degree, but in cosmology, small anomalies can signal enormous truths. This cold spot, as researchers began calling it, spanned roughly 10 degrees of sky. To put this in perspective, the full moon covers about half a degree. The cold spot was 20 times larger than the moon, a vast patch of primordial space that defied explanation. The first attempts to explain the cold spot focused on foreground contamination. Perhaps some structure between us and the cosmic microwave background was absorbing or deflecting the ancient light, creating the illusion of a cold region. Astronomers checked for intervening galaxies, dust clouds, anything that might account for the temperature deficit. They found nothing. Then they considered the opposite possibility. Perhaps the cold spot was not caused by something absorbing light, but by something missing. A void. An enormous region of space containing far fewer galaxies than average. Light passing through such a void would lose energy as it crossed, a phenomenon known as the integrated Sachs-Wolf effect. This could explain the temperature anomaly. In 2007, Lawrence Rudnick and his colleagues at the University of Minnesota analyzed radio telescope data covering the region of the cold spot. What they found sent ripples through the cosmological community. There was indeed a void there, but not just any void. A supervoid stretching nearly 2 billion light-years across. At the time, it was the largest known structure in the universe, a bubble of near emptiness so vast that its very existence challenged our understanding of how the cosmos evolved. But here is where the mystery deepens. When theorists calculated how much the supervoid could cool the cosmic microwave background, they reached an uncomfortable conclusion. The void was not large enough, not empty enough. It could account for perhaps half of the observed temperature deficit, maybe less. Something else was contributing to the cold spot, something the supervoid alone could not explain. What if the cold spot is not entirely caused by structures within our universe? What if it marks a place where our cosmos touched something else, something outside? The answer lies in a theoretical framework that most people have never heard of, yet which may contain the key to understanding our place in existence. The year was 1983. Andrei Lind, a Russian physicist working at the Lebedev Physical Institute in Moscow, published a paper that would quietly revolutionize cosmology. He called his idea eternal inflation, and it emerged naturally from the mathematics of the cosmic inflation that Alan Guth had proposed just 2 years earlier. Guth's original inflation theory was designed to solve several puzzles about the universe. Why is space so geometrically flat? Why is the cosmic microwave background so uniform? How could regions of the early universe that should never have been in contact have the same temperature? Inflation answered these questions by proposing that the universe underwent an extremely brief period of exponential expansion, stretching a tiny patch of space into everything we can observe today. But inflation required a mechanism. Something had to drive this explosive growth. Physicists proposed a hypothetical field called the inflaton field, permeating all of space and filled with tremendous energy. As the inflaton field decayed, it released its energy as matter and radiation, creating the hot, dense state we call the Big Bang. Different regions of space could undergo this decay at different times, settling down into separate pocket universes, each with its own Big Bang, its own expansion, its own cosmic history. Lind realized something profound about this process. Inflation would not stop everywhere at once. While some regions decayed and formed pocket universes, the spaces between them would keep inflating. These inflating regions would expand so rapidly that they would always dominate the total volume of existence. New pocket universes would form constantly, but the inflating background would expand faster than they could fill it. Inflation would be eternal into the future, and under certain conditions, it might be eternal into the past as well. The implications staggered the imagination. Our observable universe, everything within the 93 billion light-year sphere we can detect with our telescopes, was just one bubble among countless others. An infinite sea of cosmos surrounded us, each bubble potentially infinite in its own spatial extent, each governed by potentially different physical laws, each home to potentially different forms of matter and energy. We were not merely in a universe, we were in a multiverse. For decades, this remained a theoretical curiosity. Elegant mathematics, perhaps, but how could we ever test such a hypothesis? The other bubble universes were, by definition, beyond our observable horizon. Light from them would never reach us. Information could not cross the inflating gulf between cosmic bubbles. The multiverse seemed forever beyond the reach of scientific inquiry. Then, in 2007, another physicist had an idea that would change everything. Anthony Aguirre and Matthew Johnson, working at the University of California, Santa Cruz, asked a simple question. What would happen if two bubble universes collided? In the eternal inflation framework, each pocket universe forms when a region of the inflaton field decays to a lower energy state. This decay begins at a point and spreads outward at nearly the speed of light. creating an expanding bubble of normal spacetime within the inflating background. But here is the crucial insight. The spaces between bubbles are inflating so rapidly that most bubbles never encounter each other. They are swept apart by the exponential expansion of the background faster than their edges can grow toward each other. Most bubbles, but not all. Occasionally, purely by chance, two bubbles might nucleate close enough together that their expanding walls could actually meet. When this happened, the collision would release tremendous energy. A cosmic shockwave would propagate through both universes, leaving an imprint on their structure, and this imprint might be detectable. Aguirre and Johnson calculated what such a collision would look like from inside one of the colliding bubbles. The impact would create a circular or elliptical pattern on the cosmic microwave background, a ring of altered temperature, either hotter or colder than the surrounding radiation, marking the boundary where another universe had pressed against our own. What they found next would prove even more disturbing. When the Planck satellite released its high-precision map of the cosmic microwave background in 2013, astronomers began searching for the signatures that Aguirre and Johnson had predicted. The analysis was extraordinarily difficult. The cosmic microwave background is filled with fluctuations, random variations that could mimic the patterns expected from bubble collisions. Distinguishing a true collision signature from statistical noise required sophisticated mathematical techniques and careful attention to potential sources of contamination. In 2017, a team led by Stephen Feeney at University College London published the results of a comprehensive search. They had examined the Planck data using algorithms specifically designed to detect the circular patterns expected from cosmic collisions, and they found several candidate signals. The candidates were not conclusive. The statistical significance hovered at the edge of what scientists consider reliable evidence. The patterns could be genuine collision scars, or they could be random fluctuations that happen to resemble collision signatures by chance. More data would be needed to determine which explanation was correct, but the mere possibility sent a philosophical shockwave through the scientific community. For the first time in history, we had a method, however tentative, for detecting evidence of other universes. The multiverse was no longer purely theoretical. It had become, at least in principle, a testable hypothesis. And this brings us back to the cold spot. In 2015, another team of researchers proposed a radical explanation for the temperature anomaly that conventional physics could not fully explain. What if the cold spot was a collision scar? What if, in the very early universe, another bubble cosmos had brushed against our own, leaving a permanent bruise on the fabric of spacetime? The mathematics was suggestive. A bubble collision could indeed create a cold spot in the cosmic microwave background, depending on the relative properties of the two colliding universes. If the other bubble had different vacuum energy, different physical constants, the boundary between the two cosmos would behave in complex ways. Under certain conditions, it could produce exactly the kind of temperature deficit observed in Eridanus. The supervoid explanation had never been fully satisfactory. A collision with another universe could account for the remaining temperature anomaly that the void could not explain. We were potentially looking at evidence of something beyond the edge of everything. But here is where the mystery deepens even further. The cold spot is not the only anomaly in the cosmic microwave background. As scientists have studied the ancient light with increasingly precise instruments, they have discovered a growing list of features that do not quite fit the standard cosmological model. Patterns that seem too organized alignments that appear too perfect, asymmetries that should not exist if the universe is as uniform as we believed. The most unsettling of these anomalies is known as the axis of evil. In 2005, Kate Land and Joe Megiddo at Imperial College London published an analysis that would earn them both fame and controversy. They had been studying the largest scale patterns in the cosmic microwave background, the fluctuations that stretch across the entire sky. These fluctuations can be broken down into harmonics, much like the different frequencies that make up a complex musical note. Each harmonic represents a different spatial scale, from the vast modes that span the whole observable universe to the smaller modes that characterize individual galaxy clusters. In standard cosmology, these harmonics should be randomly oriented. The universe has no preferred direction. The largest scale fluctuations should point in random directions, bearing no relationship to each other or to structures in the nearby universe. But Land and Megiddo found something strange. The largest scale harmonics were aligned. They all seemed to point in roughly the same direction, forming an axis that stretched across the entire cosmos. Even more disturbing, this axis was aligned with the ecliptic plane of our solar system, the disk defined by Earth's orbit around the Sun. This seemed impossible. What could the largest structures in the universe possibly have to do with the orientation of a single planet orbiting an ordinary star in an unremarkable galaxy? The solar system formed billions of years after the cosmic microwave background was released. There was no conceivable physical mechanism that could connect the two. Some scientists suspected the anomaly was an artifact of the measurement process. Perhaps something about the way the satellites collected data introduced a spurious alignment related to their orbits. But careful analysis failed to identify any such systematic error. The axis of evil persisted in data from both WMAP and Planck, two completely independent satellites using different technologies and different orbits. Others proposed that the alignment was simply a statistical fluke. When you look for patterns in complex data, you will sometimes find them by chance. The cosmic microwave background contains vast amounts of information, and some apparent correlations are inevitable even in a purely random dataset. But the probability calculations were troubling. The chances of the observed alignments occurring randomly were estimated at roughly 1 in 1,000. Low, but not impossibly low, enough to raise eyebrows without demanding an explanation. This discovery was only the beginning. In 2004, another team discovered an asymmetry that seemed to divide the universe in half. The cosmic microwave background fluctuations were slightly stronger in one hemisphere of the sky than the other. The northern and southern halves of the cosmos had different statistical properties, as if something had broken the symmetry of space itself. This hemispherical asymmetry should not exist. In the standard Big Bang model, all regions of the early universe were statistically identical. The fluctuations were generated by quantum processes that should produce the same patterns everywhere. Yet the data showed a clear difference between the two cosmic hemispheres. What could cause such an asymmetry? Some physicists proposed exotic variations of inflation, models where the inflated field was not perfectly uniform, but contained subtle variations that affected different regions differently. Others suggested the asymmetry might be an imprint from before the Big Bang, a scar from a previous cosmic cycle, or a trace of structure in a larger multiverse. A few researchers proposed an even more radical explanation. What if the hemispherical asymmetry was caused by our universe being pulled in a particular direction? What if something beyond the edge of our cosmos was exerting a gravitational influence, tugging on the fabric of space-time and breaking its symmetry? This idea, sometimes called the dark flow hypothesis, would generate enormous controversy in the cosmological community, and it would point toward evidence that something immense might exist beyond the boundary of everything we can see. The dark flow story begins in 2008, when Alexander Kashlinsky at NASA's Goddard Space Flight Center led a team analyzing the motions of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, vast collections of hundreds or thousands of galaxies held together by their mutual gravity and enormous halos of dark matter. They are so massive that their movements are dominated by the largest scale structure of the cosmos. In standard cosmology, galaxy clusters should move in response to the matter distribution around them. They should be pulled toward nearby concentrations of mass and pushed away from voids. On average, these local motions should cancel out. There should be no overall drift, no cosmic current carrying the clusters in any particular direction. But Kashlinsky found something different. Using data from the WMAP satellite and X-ray observations of galaxy clusters, his team detected a coherent motion spanning a vast region of space. Hundreds of galaxy clusters, distributed across billions of light years, were all moving in roughly the same direction at velocities of several hundred kilometers per second. This motion could not be explained by the matter distribution within the observable universe. The researchers had carefully accounted for all known structures, all the galaxies and galaxy clusters and superclusters within our cosmic horizon. The dark flow remained after subtracting their gravitational effects. Something else was pulling on these clusters, something beyond the edge of what we can see. Kashlinsky proposed that the dark flow was caused by matter outside our observable universe. If the cosmos extends far beyond the 93 billion light-year sphere we can detect, then structures beyond that horizon could exert gravitational influence that we would experience as a mysterious pull in a particular direction. The galaxy clusters were not moving randomly. They were flowing towards something impossibly distant, something that would take light longer than the age of the universe to reach. The implications would shake cosmology to its core. If dark flow was real, it would mean that our observable universe is not a representative sample of the whole cosmos. The region beyond our horizon would have to be significantly different from what we can see, containing structures massive enough to pull on hundreds of galaxy clusters across billions of light years. This would challenge the cosmological principle, the assumption that the universe is statistically the same everywhere. It would suggest that we live in a special region, a local neighborhood within a much larger and more varied reality. Other scientists were skeptical. The dark flow signal was subtle, buried in noisy data. Subsequent analyses using data from the Planck satellite failed to confirm the effect with the same strength. Some researchers argued that the original detection was a statistical artifact, an apparent pattern that emerged from the complex process of subtracting foreground contamination and systematic errors. The debate continues to this day. Different teams using different methods have reached different conclusions. Some find evidence for coherent large-scale motions. Others see only random noise. The dark flow remains one of the most controversial claims in modern cosmology, neither confirmed nor definitively refuted. But even skeptics acknowledge a troubling possibility. Our methods for detecting large-scale motions may simply not be sensitive enough to see what lies beyond. The dark flow, if it exists, would be pointing us toward the edge of the known universe and the vast unknown beyond. And this raises a question that has haunted humanity since we first looked up at the stars. What if our universe has a shape? We are accustomed to thinking of space as infinite and featureless, extending forever in all directions without boundary or structure. The Big Bang did not happen at a point in space. It happened everywhere simultaneously because space itself was part of the explosion. There is no center to the universe, no edge we could approach and peer beyond. Space simply is, stretching endlessly toward infinity. But general relativity, Einstein's theory of gravity, tells us that space itself can be curved. Mass and energy bend the geometry of spacetime, creating the phenomenon we experience as gravity. On small scales, we detect this curvature directly. Light bends around massive objects. Clocks run slower in strong gravitational fields. The geometry of space is warped by everything within it. What if the entire universe is curved? Not just locally, around stars and galaxies, but globally across the whole of cosmic space. There are three possibilities. If the universe contains exactly enough matter and energy to balance its own gravity, space is flat, like an infinite plane extending forever. This is what most observations suggest. The universe appears to be flat to extraordinary precision. If the universe contains more matter and energy than this critical value, space curves back upon itself like the surface of a sphere. Such a universe would be finite in volume, but without boundary. You could travel in a straight line forever and eventually return to your starting point, just as you would if you walked in a straight line on the surface of Earth. If the universe contains less than the critical density, space curves the opposite way, like a saddle or a Pringle chip. Such a universe would be infinite in extent, but geometrically different from flat space, with parallel lines eventually diverging rather than remaining parallel. The measurements we have suggest flatness. The cosmic microwave background shows the geometric signatures of a flat universe. Light travels in straight lines on the largest scales. The angles of cosmic triangles add up to 180 degrees. But here is the crucial caveat: our measurements are not perfectly precise. There is still room for a small amount of curvature, a gentle curve that would be imperceptible on the scales we can observe, but would become significant over much larger distances. What if the universe is closed? What if we live on the three-dimensional surface of a four-dimensional hypersphere, a finite cosmos that curves back upon itself without ever encountering an edge? In 2019, a team of researchers led by Eleonora Di Valentina reanalyzed the Planck data with fresh eyes. They focused on a subtle feature of the cosmic microwave background that had been largely overlooked: the gravitational lensing of the ancient light by intervening matter. As photons from the primordial plasma travel toward us, they pass through the lumpy distribution of galaxies and dark matter that has formed over cosmic time. This matter bends their paths slightly, distorting the image of the cosmic microwave background like ripples in a pool distort the image of stones on the bottom. By measuring this lensing effect, scientists can constrain the geometry of the universe, and Di Valentino's team found something unexpected. The amount of lensing in the Planck data was slightly higher than predicted for a flat universe. The difference was small, but statistically significant. It suggested that space might be positively curved after all. The paper ignited fierce debate. Other researchers reanalyzed the same data and reached different conclusions. Some found the curvature signal compelling. Others argued it was an artifact of the analysis methods or an unfortunate statistical fluctuation. The question of cosmic geometry remains unresolved, But here is what makes this debate so profound. If the universe is closed, if space curves back upon itself like the surface of a higher dimensional sphere, then our cosmos has a finite size. There is a total volume, a countable number of galaxies, an actual amount of matter and energy that constitutes all of existence. And a finite universe raises a terrifying question. What lies beyond its boundary? Scientists had no idea what this truly meant when they first began to grasp it. We instinctively imagine the boundary of a closed universe as an edge, a wall we could approach and touch, a surface separating what is from what is not. But this intuition is wrong. The surface of a sphere has no edge. It is finite but unbounded. You can walk forever without encountering a barrier. The same would be true of a closed universe. Space would curve back upon itself so smoothly that no traveler would ever notice the curvature. You would journey in what you perceived as a straight line, crossing galaxies and superclusters and voids, and eventually you would find yourself approaching familiar territory. You would return home without ever having changed direction. There is no edge to a closed universe. No wall, no boundary, but there is something else. Something that exists outside the universe entirely, in a space that is neither within nor accessible from our cosmos. A space that contains our hypersphere the way our three-dimensional space contains the two-dimensional surface of a globe. In mathematics, this external space is called the embedding space. It is the higher dimensional arena within which a curved surface exists. For a sphere in ordinary three-dimensional space, the embedding space is simply the three-dimensional room around it. For a closed universe, the embedding space would be four-dimensional or higher, a realm of additional directions that we cannot perceive or access. Does the embedding space physically exist, or is it just a mathematical abstraction, a useful fiction that helps us visualize curved geometries without having any independent reality? This question has no easy answer. General relativity describes the internal geometry of spacetime without reference to any external space. From within the universe, there is no way to detect or measure the embedding space even if it exists. We are like ants walking on the surface of a balloon, unable to perceive the air filling its interior or the room in which it floats. But some theories suggest that the embedding space is more than mathematical convenience. String theory, the leading candidate for a quantum theory of gravity, requires extra dimensions of space beyond the three we experience. Some versions of string theory place our universe on a membrane, a higher dimensional surface floating in a vast bulk space that may contain other membranes, other universes, other realities. And this brings us to a concept that might be the key to understanding what lies beyond everything we know: the brain world. In 1999, Lisa Randall and Raman Sundram, two physicists at Princeton University, proposed a radical new model of reality. They suggested that our universe is a three-dimensional membrane embedded in a higher dimensional space. This membrane, or brain, contains all the matter and energy we can detect. Photons, electrons, quarks, everything that makes up the observable cosmos is confined to the brain like ink on a sheet of paper. But gravity is different. In the Randall-Sundram model, gravity can leak off the brain and propagate through the higher dimensional bulk. This explained a long-standing puzzle in physics: why gravity is so much weaker than the other fundamental forces. Perhaps gravity is not intrinsically weak. Perhaps it only appears weak because most of its strength is spreading into dimensions we cannot perceive. The model made specific predictions. The strength of gravity should change in particular ways at very short distances. Particles colliding at high energies might occasionally disappear into the extra dimensions. The signatures of the bulk might be detectable with sufficiently precise experiments. Physicists at the Large Hadron Collider searched for evidence of extra dimensions. They looked for microscopic black holes that would form if gravity became stronger at short distances. They hunted for missing energy signatures that would indicate particles escaping into the bulk. They found nothing. The extra dimensions, if they exist, are hidden more cleverly than the simplest models predicted. But absence of evidence is not evidence of absence. The Randall-Sundrum model and its variants remain viable possibilities, consistent with all observations, waiting for more sensitive experiments that might finally reveal the truth. And here is where the brain-world concept becomes truly mind-expanding. If our universe is a membrane in a higher dimensional space, then other membranes might exist. Parallel branes floating in the bulk, separated from us by distances along dimensions we cannot perceive. These other branes could be entire universes in their own right, complete with their own matter, their own energy, their own laws of physics. We would never be able to see these other branes directly. Light is confined to our membrane and cannot travel through the bulk, but gravity leaks between branes. If another brane passed close to ours, we might detect its gravitational influence. We might feel a pull from matter that exists in a parallel reality, a tug from galaxies in another universe brushing past our own. Could this explain the dark flow? Could the coherent motion of galaxy clusters be caused by a neighboring brane exerting gravitational attraction from across the extra dimensions? Could the cold spot be a scar from a brane collision, a place where another universe touched ours and left a permanent bruise on the cosmic microwave background? These questions remain unanswered. The mathematics of brane cosmology is complex and still being developed. Many possibilities exist within the theoretical framework, and we do not yet know which, if any, corresponds to reality. But one thing is becoming clear. The question of what lies beyond the edge of everything is no longer purely philosophical. It has become a scientific question, one that we are beginning to develop tools to address. And the answers we are finding suggest that our universe may be far stranger, far larger, and far less lonely than we ever imagined. The journey continues. When we ask what lies beyond the universe, we are implicitly assuming that beyond has meaning. We are assuming that space extends past some boundary, that there is a there out there, a place where the universe ends and something else begins. But this assumption may be wrong. Consider the nature of space itself. In general relativity, space is not a pre-existing arena within which events unfold. Space is a feature of the universe, part of the physical content of reality. Space came into being with the Big Bang. It expands as the universe expands. It is shaped by the matter and energy it contains. If space is part of the universe, then asking what lies outside the universe is like asking what is north of the North Pole. The question sounds meaningful, but it has no answer because it contains a hidden category error. North is defined relative to the Earth's surface. Once you reach the pole, north ceases to have meaning. Similarly, outside is defined relative to space. If space ends at the boundary of the universe, outside ceases to have meaning there. Some physicists take this view. The universe is all of physical reality. There is no outside because outside requires space, and space exists only within the universe. The question of what lies beyond is not mysterious. It is simply malformed. But other physicists disagree. They argue that even if our particular space began with our particular Big Bang, other spaces might exist independently. The multiverse models of eternal inflation create bubble universes with their own distinct spaces, their own distinct times, their own distinct geometries. These bubbles are not outside our universe in the ordinary spatial sense, but they exist in some larger sense, as part of a vaster structure that transcends any single cosmos. And here is the truly dizzying possibility. That larger structure might itself be embedded in something even larger, and that larger structure in something larger still. Levels upon levels of reality, each one containing what came before as a small component, an infinitesimal bubble, a mote of existence within a vast hierarchy of being. Where does it end? Does it end? These questions push against the limits of human comprehension. Our minds evolved to navigate the African savanna, to track predators and find food and raise children. We are not built to contemplate infinite regresses, higher dimensions, or the structure of structures that contain all possible structures. But we try anyway. That is what makes us human. And in trying, we have discovered something remarkable. The universe, for all its vastness, for all its mystery, for all its apparent indifference to human concerns, is comprehensible. The same mathematics that describes the arc of a thrown stone describes the orbit of galaxies around each other. The same physical laws that govern atoms in a laboratory govern stars at the edge of the observable cosmos. This comprehensibility is itself a mystery. Why should a universe that existed for billions of years before us, that will exist for billions of years after us, that extends far beyond anything we can ever visit or touch, be describable by equations that fit on a blackboard? Why should the deep structure of reality correspond to patterns that human minds can grasp? Some see in this correspondence evidence of design, a universe created with mathematical elegance by an intelligence that transcends creation. Others see natural selection, a process by which minds that can model reality accurately are more likely to survive and reproduce. Still others see nothing more than happy coincidence, a brute fact about existence that requires no explanation. Whatever the reason, we find ourselves in a universe we can partially understand. And that partial understanding has led us to the edge of everything we know, and perhaps beyond. What awaits us there? This question will guide us through the rest of our journey. We will examine the evidence from the cosmic microwave background, the motions of galaxies, the geometry of space itself. We will explore the theoretical frameworks that attempt to explain what might exist beyond, from the multiverse to brain cosmology to even stranger possibilities. We will confront the limits of knowledge itself, the boundaries beyond which science cannot yet penetrate, and throughout, we will grapple with the existential implications. What does it mean for humanity if we are one bubble among infinite bubbles? How should we understand our place in a reality so vast that our entire cosmos might be an insignificant speck within it? These questions have no easy answers, but they are worth asking. They are worth pursuing. They are worth the effort of minds that can barely comprehend their own existence, reaching out to grasp the nature of everything. The edge of the universe is not a place we can visit. It is not a wall we can touch or a boundary we can cross. It is the limit of our knowledge, the frontier where certainty ends and mystery begins. But frontiers are meant to be explored, and we are just getting started. The year was 1998, and two teams of astronomers were about to discover something that would overturn everything we thought we knew about the fate of the universe. They were hunting for distant supernovae, exploding stars that briefly outshine entire galaxies before fading into darkness. These cosmic explosions served as standard candles, objects of known brightness that could be used to measure the distances to far-flung galaxies with unprecedented precision. The goal was straightforward. By measuring how fast distant galaxies were receding and how far away they were, The astronomers hoped to determine the ultimate destiny of the cosmos. Was the universe expanding fast enough to escape its own gravity and expand forever? Or would the gravitational pull of all that matter eventually slow the expansion, halt it, and reverse it into a final cosmic collapse? The answer they expected was somewhere in between. The expansion should be slowing down, they assumed, as gravity gradually applied the brakes. The only question was how much. But when the data came in, both teams found something impossible. The expansion of the universe was not slowing down at all. It was speeding up. Galaxies were flying apart from each other faster and faster as time went on. Something was pushing the cosmos apart, overwhelming the attractive force of gravity and driving space itself to expand at an accelerating rate. That something came to be called dark energy, and it constitutes roughly 68% of the total energy content of the universe. We had discovered that most of reality was made of something we did not understand. Dark energy behaves unlike any form of matter or energy we have ever encountered. Instead of diluting as space expands, as ordinary matter and radiation do, dark energy maintains a constant density. Every cubic meter of space contains the same amount of dark energy, no matter how much the universe stretches. As space expands and new volume is created, new dark energy appears to fill it. The more space there is, the more dark energy there is, and the stronger the accelerating push becomes. The simplest explanation is that dark energy is a property of space itself. Einstein actually predicted something like this in 1917 when he introduced the cosmological constant into his equations of general relativity. He added the term to balance gravity and create a static universe, which was what astronomers believed in at the time. When Hubble discovered the expansion, Einstein abandoned the cosmological constant, calling it his greatest blunder. But the 1998 discovery vindicated Einstein in an unexpected way. The cosmological constant was real after all. Space itself possessed an intrinsic energy that pushed outward, opposing the inward pull of gravity. The universe was not just expanding, it was being actively driven apart by the very fabric of reality. Here is where the mystery deepens into something truly unsettling. When physicists tried to calculate the expected value of the cosmological constant using quantum field theory, they got an answer that was wrong by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. It is the worst prediction in the history of physics. The observed value of dark energy is not just different from the theoretical expectation. It is smaller by an incomprehensible margin, as if some unknown mechanism was canceling out nearly all of the vacuum energy that should exist. Why should the cosmological constant have this particular value? A slightly larger value would have caused the universe to expand so rapidly that galaxies could never form. A slightly smaller value, or a negative value, would have caused the universe to collapse before stars had time to ignite. The observed value is exquisitely fine-tuned for the existence of complex structures, for galaxies and planets, and ultimately for life. This fine-tuning problem has led some physicists to embrace a radical solution. Perhaps the cosmological constant is not the same everywhere. Perhaps different regions of space, different pocket universes within the eternal inflation framework have different values of dark energy. Most of these universes would be sterile, either expanding too fast or collapsing too quickly to produce anything interesting. But a few would have values compatible with structure formation. And we, by necessity, would find ourselves in one of those rare habitable universes. This is the anthropic principle applied to cosmology. We observe a universe fine-tuned for our existence, not because the universe was designed for us, but because we could not exist in any other kind of universe. The cosmological constant has the value it does because that value allows observers to exist, and observers can only observe universes that produce them. Many scientists find this reasoning unsatisfying. It feels like giving up, like abandoning the search for a deeper explanation in favor of a statistical coincidence. But if the multiverse is real, if eternal inflation truly creates an infinite ensemble of pocket universes with varying properties, then the anthropic explanation may be the only one available. And this has profound implications for what might exist beyond the edge of our universe. If dark energy varies from universe to universe, then the cosmos surrounding ours might be radically different from what we experience. Some neighboring universes might have such large cosmological constants that they are essentially empty, expanded to oblivion before any structure could form. Others might have collapsed into singularities almost immediately after their birth. Still others might have negative cosmological constants, existing in perpetual contraction, perhaps cycling endlessly through big bangs and big crunches. Our universe, with its particular value of dark energy, sits in a narrow habitable band within a vast landscape of possibilities. We are not typical. We are not average. We are the survivors, the rare bubbles of cosmos that happen to have the right properties for complexity to emerge. But what exactly is dark energy? What is its ultimate nature? This remains one of the deepest unsolved problems in physics. The cosmological constant interpretation assumes that dark energy is truly constant, unchanging throughout cosmic history. But observations have not ruled out the possibility that dark energy varies over time, that it was different in the past and will be different in the future. If dark energy is not constant, if it is a dynamic field that evolves as the universe ages, then the future of the cosmos becomes uncertain. Some models predict that dark energy will grow stronger over time, eventually tearing apart not just galaxies, but stars, planets, atoms themselves in a catastrophic Big Rip. Others suggest that dark energy will eventually decay, perhaps transitioning to a different value that could trigger another period of inflation or even a collapse. The fate of the universe hangs on the nature of dark energy, and we do not know what dark energy is. This ignorance should humble us as we contemplate what lies beyond the edge of everything. We do not fully understand even the dominant component of our own universe. We observe its effects without grasping its cause. We measure its influence without comprehending its essence. If we are so ignorant about what fills the space we can observe, how can we hope to understand what might exist beyond? And yet we push forward. We ask the questions even when the answers seem impossibly remote. That is the nature of science. That is the nature of human curiosity. What they found next would prove even more disturbing than the mystery of dark energy itself. In the early 2000s, cosmologists began constructing detailed maps of the large-scale structure of the universe. They used galaxy surveys to chart the positions of millions of galaxies, tracing the cosmic web of filaments and voids that matter had formed over billions of years. They used the cosmic microwave background to peer back to the earliest epochs, when the seeds of all future structure were just beginning to form. And they discovered that the universe was lumpy in ways that strained the standard model. The problem centered on something called sigma-8, a parameter that describes how strongly matter clumps together on scales of about 8 megaparsecs, roughly 26 million light-years. The cosmic microwave background, which captures the state of the universe 380,000 years after the Big Bang, implied a certain value for sigma 8. Observations of the modern universe, 13.8 billion years later, implied a slightly different value. The difference was small but persistent. Different measurement techniques gave inconsistent results. The early universe predicted slightly more clumping than the late universe displayed. Something was causing matter to cluster less efficiently than expected. This became known as the sigma 8 tension, and it joined a growing list of discrepancies that threatened to crack the foundations of standard cosmology. The Hubble tension, a disagreement about the current expansion rate of the universe, showed similar patterns. Measurements based on the early universe gave one answer. Measurements based on the local universe gave another. The two answers did not match. These tensions might be statistical flukes, the result of systematic errors in the data or unknown sources of contamination. But they might also be pointing toward new physics, new phenomena that the standard cosmological model fails to capture. Some researchers proposed that the discrepancies could be explained by modifying dark energy, allowing it to vary in ways that would reconcile the early and late universe measurements. Others suggested modifications to gravity itself, departures from general relativity that would become significant only on the largest cosmic scales. Still others pointed to the possibility that the universe contains components we have not yet detected, additional forms of matter or energy that influence cosmic evolution in subtle ways. And a few researchers raised an even more radical possibility. What if the tensions are not caused by anything within our universe at all? What if they are signs of influence from beyond? If our universe is embedded in a larger structure, if other universes or higher dimensional spaces interact with our cosmos through gravity or other forces, those interactions might manifest as subtle anomalies in our measurements. The tugging of matter in other brains, the imprint of bubble collisions, the influence of structure in the embedding space, all of these could create discrepancies between what we expect and what we observe. We have no direct evidence for such explanations. They remain speculative, at the fringe of mainstream cosmology, but the mere fact that they are being seriously discussed illustrates how profoundly our view of reality is shifting. The universe is no longer a closed system. It is potentially open to influences from beyond, connected to a larger reality that we are only beginning to glimpse. The evidence for this larger reality comes from many directions. Let us turn now to one of the most compelling, the study of black holes and what they might reveal about the structure of existence itself. Black holes are the universe's most extreme objects. They form when massive stars collapse at the end of their lives, compressing their core into a region so dense that nothing, not even light, can escape the gravitational pull. The boundary surrounding this region is called the event horizon. Once anything crosses the event horizon, it is lost to the outside universe forever, or so we thought. In 1974, Stephen Hawking discovered something remarkable about black holes. Applying quantum mechanics to the curved spacetime near the event horizon, he found that black holes were not truly black. They emitted a faint glow of radiation, now called Hawking radiation, as quantum fluctuations near the horizon allowed particles to escape into space. This radiation came at a cost. Every photon that escaped carried away a tiny amount of energy, and that energy came from the black hole itself. Over immense timescales, black holes would slowly evaporate, shrinking bit by bit until they finally vanished entirely. This discovery created a crisis in physics that remains unresolved today. The information paradox. When matter falls into a black hole, what happens to the information it carries? The quantum state of every particle, every detail about what fell in, is apparently locked behind the event horizon forever. But if the black hole eventually evaporates through Hawking radiation, and if that radiation is purely thermal, carrying no information about what formed the black hole, then information seems to be destroyed. This violates a fundamental principle of quantum mechanics. Information is never supposed to be lost. The quantum state of any system should always be recoverable in principle. If black holes destroy information, then the foundations of physics would need to be rebuilt. Physicists have proposed many solutions to the information paradox, and several of them have profound implications for the nature of reality and what might exist beyond our universe. One proposal suggests that information is not destroyed, but gradually encoded in the Hawking radiation through subtle correlations. Another proposes that information is stored on the event horizon itself, encoded in a holographic form that is eventually released as the black hole evaporates. Still, another suggests that black holes do not truly evaporate, but leave behind remnants that preserve the information indefinitely. But the most radical proposal suggests something extraordinary about the interior of black holes themselves. In the 1960s, physicists exploring the mathematics of rotating black holes discovered something strange. The equations seemed to describe not just the black hole itself, but a passage to somewhere else, a wormhole, a tunnel through space-time connecting distant regions of the universe, or perhaps connecting different universes entirely. These wormhole solutions were initially dismissed as mathematical curiosities. The interior of a real black hole would be chaotic and unstable, filled with quantum fluctuations that would destroy any traveler long before they could reach whatever lay on the other side. The singularity at the center, where space-time curvature becomes infinite, represented a breakdown of physics itself, a place where the equations cease to make sense. But in recent years, a different picture has emerged. Some physicists now believe that singularities do not actually exist. Quantum effects become important as matter approaches infinite density, and those effects might prevent the singularity from forming. Instead of crushing matter into a point of infinite density, the extreme conditions inside a black hole might trigger a bounce, a reversal of the collapse that sends matter expanding outward. Outward into what? Perhaps into a new universe. This idea, sometimes called cosmological natural selection, was developed by physicist Lee Smolin in the 1990s. He proposed that the interior of every black hole might give birth to a new cosmos, a baby universe that inflates and expands and eventually forms its own stars and galaxies and black holes. Those black holes would in turn give birth to more universes. The multiverse would reproduce, with each generation inheriting slightly modified physical constants from its parent. Over countless generations, this cosmic reproduction would favor universes that produce many black holes, because those universes would have more offspring. The physical constants we observe, the masses of particles, the strengths of forces, the value of the cosmological constant, would all be tuned by this evolutionary process to maximize black hole production. It is a strange and speculative idea, but it makes a testable prediction. The physical constants of our universe should be close to optimal for producing black holes. Any small change in the constants should reduce the number of black holes that form. Some physicists have argued that this prediction is roughly satisfied. The universe does seem to produce black holes efficiently. Small changes to the physical constants do seem to reduce star formation and therefore black hole formation. But the evidence is far from conclusive. Hypothesis remains controversial, unproven, at the edge of scientific respectability. What is not controversial is the profound philosophical implication. If Smolin's idea is correct, then our universe is not merely surrounded by other universes. It is one link in an infinite chain of cosmic reproduction, a child of an older universe, a parent to countless universes yet to be born. The black holes we observe are not just extreme objects within our cosmos. They are birthplaces, portals to new realities, wombs of creation. And this suggests something remarkable about the nature of existence itself. Reality might be fundamentally creative, constantly giving birth to new forms, new spaces, new possibilities. The edge of everything might not be a boundary at all, but a threshold, a door to endless becoming. The implications would shake our understanding of reality to its core. Let us turn now to an even stranger possibility. What if our universe is not made of matter at all? What if everything we experience, every particle and every force, is actually information? This idea has deep roots in physics. In the 1970s, Jacob Bekenstein discovered that black holes have entropy, a measure of disorder or hidden information. The entropy of a black hole is proportional not to its volume, as one might expect, but to the surface area of its event horizon. This suggested that all the information about the black hole's interior was somehow encoded on its two-dimensional boundary. This insight led to the holographic principle, one of the most profound ideas in theoretical physics. It proposes that the information content of any region of space can be fully described by data on its boundary. A three-dimensional volume is equivalent to a two-dimensional surface. The universe might be a hologram. In 1997, Juan Maldacena discovered a precise mathematical realization of this principle. He showed that a particular theory of gravity in a five-dimensional curved spacetime was exactly equivalent to a quantum field theory living on the four-dimensional boundary of that space. The bulk and the boundary were two descriptions of the same physics, two languages for the same reality. This correspondence, known as AD-SCFT, has become one of the most important tools in theoretical physics. It has been used to study black holes, quantum entanglement, and even strongly interacting systems in condensed matter physics. It provides concrete evidence that the holographic principle is more than a metaphor. The universe might genuinely be holographic at its deepest level. But here is where the implications become truly strange. If the universe is a hologram, then the three-dimensional space we experience is not fundamental. It is emergent, arising from information encoded on a distant boundary. Our sense of depth, of volume, of spatial separation is an illusion, a projection from a lower dimensional reality that is more fundamental than anything we can directly perceive. Where is this boundary? In the AD-SCFT correspondence, it lies at the edge of spacetime, infinitely far away in a technical sense. But our universe is not anti-de Sitter space. It is described by a different geometry, an expanding cosmos with positive cosmological constant. The holographic principle should still apply, but its precise formulation remains elusive. Some researchers believe that the holographic boundary of our universe lies at the cosmological horizon, the edge of the observable cosmos beyond which light can never reach us. Others propose that the boundary is the Big Bang itself, the initial singularity from which space and time emerged. Still others suggest that the boundary lies in the future, at the ultimate fate of the cosmos. Wherever the boundary is, the holographic principle implies that it contains complete information about everything within. Every particle in your body, every thought in your mind, every event in cosmic history is encoded on a distant surface that you can never reach or perceive directly. You are a projection, a shadow, a pattern of information cast inward from the edge of everything. This is not mysticism or metaphor. This is the direction that theoretical physics is pointing, based on rigorous mathematical analysis of black holes, quantum gravity, and the structure of space-time itself. And it suggests an extraordinary possibility about what lies beyond the edge of everything. Perhaps beyond is the wrong question. Perhaps the edge is everything. Perhaps the boundary contains all the information, and what we call the universe is just one way of reading that information, one projection among many possible projections. Other projections might exist, other ways of reading the boundary data, other universes emergent from the same fundamental information. We might not be alone in the hologram. The journey into the unknown continues to reveal deeper and deeper layers of mystery. Each answer we find raises more questions. Each discovery expands the horizon of our ignorance. Let us now consider time itself and what it might reveal about the nature of existence beyond our universe. We experience time as a river flowing ever forward from past to future. The past is fixed, unchangeable, accessible only through memory. The future is open, undetermined, full of possibility. The present is the boundary between them, the moving edge of reality where existence happens. But physics tells a different story. In the equations of general relativity, time is not fundamentally different from space. Both are dimensions of a unified entity called space-time. Events do not happen in time, they simply exist at particular locations in the four-dimensional block of space-time. Past, present, and future all exist simultaneously. The flow of time is an illusion, a consequence of how conscious beings experience the static structure of reality. This is the block universe interpretation, and it suggests something profound about the nature of existence. If all of time exists at once, then the Big Bang is not something that happened in the past. It exists at one end of the space-time block, and whatever lies beyond the universe, whatever larger structure might contain our cosmos, would exist not before or after our universe, but alongside it, in dimensions or regions that transcend our particular slice of space-time. But not all physicists accept the block universe. Some argue that the future is genuinely open, that quantum mechanics introduces fundamental indeterminacy that cannot be captured in a static block. Others propose that time is emergent, arising from more fundamental timeless structures at the Planck scale. Still others suggest that time itself might have begun with the Big Bang, making questions about before the Big Bang meaningless. In 2013, Julian Barber and his collaborators proposed a radical new picture of time's origin. They suggested that time might have two directions, flowing forward in our universe and backward in a mirror universe that exists on the other side of the Big Bang. At the moment of the Big Bang, time would split, creating two arrows pointing in opposite directions from a common origin. In this picture, our universe and its mirror twin would be connected at their origins, two halves of a single structure that spans the singularity. Observers in the mirror universe would experience time flowing in the opposite direction, but from their perspective, everything would seem normal. They would see their own past behind them and their own future ahead, never suspecting that they were moving backward relative to us. This is a speculative idea, unsupported by direct evidence. But it illustrates how profoundly our understanding of time might need to change as we probe the deepest questions about reality. And it suggests yet another way that something might exist beyond the edge of everything. Beyond might not mean farther in space or later in time. Beyond might mean in directions we cannot perceive, in dimensions of time or space that lie perpendicular to the ones we experience. Our universe might be a single slice of a higher dimensional block. Other slices might exist nearby, containing their own realities, their own cosmic histories, their own forms of existence. What would it mean to step outside of time itself? To perceive the block universe from outside, the way we perceive a three-dimensional object from our position in three-dimensional space? We cannot imagine such a perspective. Our minds are embedded in time, constituted by processes that unfold moment by moment. To step outside of time would be to become something utterly unlike a human consciousness, something that encompasses past and future in a single eternal now. Perhaps this is what lies beyond the edge of everything, not another place or another time, but a perspective so alien that it transcends place and time altogether. These speculations might seem to have departed from science into philosophy or mysticism, but they emerge naturally from our best theories of physics. They are the implications that physicists themselves draw when they take their equations seriously, and they remind us that the question of what lies beyond the universe is not just a question about space or cosmology. It is a question about the nature of existence itself, about the structure of reality at its deepest level, about the limits of what can be known and understood. We have traveled far in our exploration. We have encountered the cosmic microwave background and its mysterious anomalies. We have traced the implications of eternal inflation and the multiverse. We have explored brain worlds and holographic principles and the strange interior of black holes. We have questioned the nature of time itself, but our journey is not complete. There remain phenomena we have not yet examined, theories we have not yet considered, possibilities we have not yet imagined. The universe continues to reveal new mysteries. And each mystery points beyond itself, toward a larger reality that we are only beginning to glimpse. Let us continue our descent into the unknown. In the early universe, in the first fraction of a second after the Big Bang, the cosmos was filled with a dense plasma of particles and radiation. This plasma was opaque, constantly scattering light like fog scatters a flashlight beam. No information could travel freely through this primordial murk, but the plasma was not uniform. Quantum fluctuations during the inflationary epoch had imprinted tiny variations in density, regions slightly denser or slightly less dense than average. These variations were the seeds of all future structure. Denser regions would eventually collapse under their own gravity, forming galaxies and clusters of galaxies. Less dense regions would become the great voids that separate the cosmic web. In the plasma phase, these density variations could not grow freely. Radiation pressure counteracted gravity, preventing the denser regions from collapsing. Instead, the plasma oscillated like sound waves rippling through a fluid. Denser regions compressed, then rebounded, then compressed again. The entire universe rang like a bell, with density waves propagating through the primordial medium. These oscillations left their imprint on the cosmic microwave background. When the universe cooled enough for atoms to form, the plasma became transparent and the density waves froze in place. The pattern of compressions and rarefactions became a permanent record, encoded in the temperature variations of the ancient light. By analyzing these temperature variations, cosmologists can extract extraordinary information about the early universe. The specific pattern of peaks and valleys in the power spectrum reveals the geometry of space, the density of matter, the ratio of ordinary matter to dark matter, the epoch when atoms formed. It is like studying the overtones of a ringing bell to determine its size and shape and composition. And this analysis has revealed something remarkable about the initial conditions of the universe. The quantum fluctuations that seeded all structure were almost perfectly Gaussian, meaning they followed the simplest possible statistical distribution. They were almost perfectly scale invariant, meaning they had the same amplitude on all spatial scales. They were almost perfectly adiabatic, meaning they affected all types of matter and radiation equally. These properties are not required by the laws of physics. Many other initial conditions were possible. The fluctuations could have been non-Gaussian, with complex correlations that would have produced a very different cosmic web. They could have had a spectrum that favored some scales over others, producing a universe dominated by structures of a particular size. They could have been isocurvature, affecting different types of matter differently. But the observed fluctuations have exactly the properties predicted by the simplest versions of cosmic inflation. This is strong evidence that inflation actually occurred, that the universe really did undergo a brief period of exponential expansion in its first moments. And as we have seen, inflation leads naturally to the multiverse. Once inflation begins, it never completely stops. Our universe is one bubble among countless others, each nucleating from the inflating background, each evolving independently, each potentially giving rise to its own stars and galaxies and observers. The cosmic microwave background is not just a window into the early universe. It is a window into the mechanism that created the multiverse itself. By studying its properties in ever finer detail, we might eventually find signatures that go beyond standard inflation. Signatures of bubble collisions, signatures of cosmic strings, signatures of the larger structure within which our cosmos is embedded. This is why the anomalies we discussed earlier are so tantalizing. The cold spot, the axis of evil, the hemispherical asymmetry. Each of these might be a statistical fluke, noise in the data that happened to form suggestive patterns, but each might also be a genuine signal, a message from beyond the edge of everything. The stakes could not be higher. If any of these anomalies prove to be real, to be caused by physics beyond the standard model, we would gain our first empirical evidence of what lies outside our universe. We would know that we are not alone. The search for such evidence continues. New satellites are being designed to map the cosmic microwave background with even greater precision. New telescopes are being built to survey the large-scale structure of the universe with unprecedented detail. New theoretical frameworks are being developed to predict what signatures we should look for and how to distinguish them from noise. Within a generation, we might have answers. Or we might discover that the universe guards its secrets more jealously than we hoped, that the evidence we seek is forever beyond our reach. Either way, the journey is worth taking. The questions are worth asking. The mystery is worth pursuing, because this is what humans do. We stare into the darkness and ask what lies beyond. We reach beyond the edge of our knowledge and grasp for understanding. We are the universe contemplating itself, the cosmos becoming conscious of its own existence. And that consciousness drives us onward, ever onward, into the unknown. Let us turn now to one of the strangest and most challenging ideas in modern physics. The possibility that our universe is not unique because it is one of many, but because it is one of infinitely many copies of exactly the same cosmos. This idea emerges from the mathematics of an infinite universe. If space extends forever, and if the laws of physics are the same everywhere, then everything that can happen will happen. Every possible arrangement of atoms, every possible configuration of matter will be realized somewhere in the infinite expanse, including exact copies of you. Somewhere, inconceivably far away, there is another Earth, another version of your city, your street, your home, another version of you reading these exact words at this exact moment. The copy is identical in every detail, down to the last neuron firing in your brain. Beyond that copy lies another, with one small difference. A single bit flipped, a single choice made differently, a single event unfolding in a slightly altered way. Beyond that lies another, with two differences. And so on, through all possible variations, all possible lives, all possible versions of everything that could ever be. This is the level 1 multiverse, the simplest kind of parallel reality. It requires no exotic physics, no higher dimensions, no bubble universes. It follows directly from the assumption that space is infinite and uniform. The distances involved are staggering. Your nearest identical copy is estimated to be roughly 10 to the 10 to the 29 meters away. That is a number so large that writing it out would require more digits than there are atoms in the observable universe. It is far beyond anything we could ever observe or reach. But if the universe is truly infinite, that distance is nothing. It is less than a speck compared to the endless expanse of space. Many physicists find this conclusion absurd. Surely something must limit the universe, they argue. Surely space must curve back upon itself, or end at some boundary, or behave differently in regions we cannot see. The idea of infinite identical copies seems more like fantasy than physics, but the mathematics is unambiguous. If the universe is infinite and uniform, the copies exist. The only escape is to deny one of the premises. Perhaps the universe is not infinite. Perhaps space is closed, curving back upon itself so that the total volume is finite. In that case, the number of possible configurations is still vast but not truly infinite. Exact copies would not be guaranteed. Perhaps the universe is not uniform. Perhaps the laws of physics vary from place to place, or the initial conditions differed in distant regions. In that case, the argument about inevitable copies would break down, or perhaps our understanding of what it means for something to exist needs revision. Perhaps existence is not absolute but relative, depending on perspective or definition in ways we have not yet grasped. These are deep waters, and we have not reached the bottom. The question of whether infinite copies of you exist somewhere in the cosmos is not currently answerable. It may never be answerable. But the mere possibility reshapes how we think about identity, consciousness, and the nature of existence. If there are infinitely many versions of you, which one is really you? Are you all of them? None of them? The question of personal identity becomes profoundly strange in an infinite multiverse. And this brings us to an even deeper puzzle, the nature of consciousness itself and what it might reveal about the structure of reality. Consciousness is the one phenomenon we know with absolute certainty. We can doubt the existence of the external world. We can question whether other minds exist. We can wonder whether our memories are reliable or our perceptions accurate. But we cannot doubt that we are experiencing something. The fact of experience is undeniable, even if everything else is illusion. Yet consciousness remains the greatest mystery in science. We have no explanation for how physical processes in the brain give rise to subjective experience. We have no theory of why there is something it is like to be you rather than nothing at all. The gap between the objective description of neural activity and the subjective reality of felt experience seems unbridgeable. Some philosophers argue that consciousness is fundamental, not derived from or reducible to physical processes. It is a basic feature of reality, like space or time or mass. Perhaps consciousness pervades the universe, present in some form in every physical system. This view is called panpsychism, and it has been defended by serious thinkers from ancient times to the present. If consciousness is fundamental, then it might play a role in determining the nature of reality itself. The laws of physics might not be the only laws that govern existence. There might be laws of consciousness, principles that determine how experience arises and what forms it can take. And here is where the speculation becomes truly wild. Some researchers have proposed that consciousness might be connected to the foundations of quantum mechanics. The measurement problem in quantum physics, the puzzle of how the act of observation seems to collapse the wave function, might involve consciousness in some deep way. Perhaps consciousness is not just a passive observer of reality, but an active participant in bringing reality into being. This idea is controversial and largely rejected by mainstream physics, but it refuses to die. Each generation of physicists and philosophers revisits it, drawn by the persistent mystery of how subjective experience could possibly exist in a universe of objective physical law. If consciousness does play a fundamental role in reality, then the question of what lies beyond the edge of everything takes on new dimensions. Beyond might not just mean other regions of space or other pocket universes. Beyond might mean other forms of consciousness, other modes of experience, other ways of being. Perhaps the multiverse is not just a collection of physical realms, but a spectrum of conscious experiences. Perhaps what lies beyond our universe is not more matter and energy, but more minds, more ways of experiencing existence, more perspectives on being. These ideas are not science. They are speculation, philosophy, perhaps poetry, but they emerge from our struggle to understand the deepest questions about existence. They represent the furthest reaches of human thought, the edge of everything we can imagine, and they remind us that the universe might be stranger than we can suppose. The mystery might run deeper than we know. The edge of everything might not be where we expected to find it. We continue our descent into the unknown. Let us return to more solid ground and consider what we have learned and what remains unknown. The evidence we have examined points toward a cosmos far larger and stranger than anything our ancestors imagined. The universe we observe, the 93 billion light-year sphere accessible to our telescopes, is almost certainly not all that exists. Theoretical physics suggests that our cosmos is one bubble among countless others, one brain in a higher dimensional space, one projection from a holographic boundary. The anomalies in the cosmic microwave background, the unexplained acceleration of the cosmos, the puzzling discrepancies between different measurements, all hint at physics beyond the standard model. Some of these anomalies might be explained by new particles or forces within our universe, but some might be signs of influence from beyond, signatures of the larger structure within which our cosmos is embedded. We cannot yet distinguish between these possibilities. The evidence is tantalizingly suggestive, but frustratingly inconclusive. We are like archaeologists who have found a few potsherds and are trying to reconstruct an entire civilization. We have fragments of the truth, but the full picture remains hidden. What would it take to go further? What evidence would convince us that something lies beyond the edge of everything? The most compelling evidence would be a clear signature of a bubble collision, an unmistakable pattern in the cosmic microwave background that could not be explained by any physics within our universe. Several candidate signals have been identified, but none has reached the threshold of statistical certainty that would convince skeptics. Gravitational waves might provide another window. If bubble collisions or brain interactions generate gravitational waves, those waves might be detectable by future observatories. The LIGO and Virgo experiments have already detected gravitational waves from black hole mergers and neutron star collisions. Future space-based observatories like LISA might be sensitive to the primordial gravitational wave background, including any signals from exotic cosmological events. Particle physics could also contribute. If our universe is embedded in a higher dimensional space, the extra dimensions might manifest in the behavior of particles at extremely high energies. The Large Hadron Collider has searched for such signatures without success, but future colliders with even higher energies might find what we are looking for, or the evidence might come from a direction we have not anticipated. The history of physics is filled with surprises, with discoveries that no one predicted. Dark energy was not expected. The cosmic microwave background was not predicted until shortly before its discovery. The expansion of the universe was a shock when Hubble first observed it. The universe has repeatedly proven itself stranger than our theories. Whatever evidence eventually emerges, we should approach it with humility. Our current understanding is incomplete. Our theories are provisional. The history of cosmology is littered with ideas that seemed compelling in their time, but were later overturned. We should hold our beliefs lightly, ready to revise them when new evidence demands it. But we should also not be paralyzed by uncertainty. The fact that we might be wrong should not stop us from seeking the truth. Science progresses by making bold conjectures and then testing them ruthlessly. Some conjectures will fail. That is the price of discovery. The conjecture that something lies beyond our universe is bold indeed. It challenges our intuitions about the nature of existence. It suggests that everything we know and love, everything that has ever happened in cosmic history, might be an infinitesimal fraction of a larger reality. But boldness is appropriate when addressing the deepest questions. The question of what lies beyond the edge of everything is the deepest question we can ask. It encompasses all other questions. It leads us to the ultimate nature of existence itself, and we are making progress. Slowly, haltingly, with many false starts and dead ends, we are assembling a picture of reality that extends beyond our cosmic horizon. We are learning to ask the right questions, to develop the right tools, to interpret the evidence that the universe provides. The edge of everything is receding before us, revealing new landscapes of possibility. We cannot see to the end. We may never see to the end, but we are on the journey, and the journey matters, because this is what it means to be human. To wonder, to question, to seek, to refuse to be satisfied with the boundaries of the known, to reach beyond the edge of everything, grasping for the truth that lies in the darkness. And whatever we find there, whatever answers or further mysteries await, the search itself ennobles us. It connects us to something larger than our individual lives. It makes us participants in the cosmic process of self-discovery. The universe is waking up. Through us, through our questions and our instruments and our theories, existence is coming to know itself. We are the cosmos made conscious, peering beyond the edge of everything, seeking what lies on the other side. And the journey continues. The search for what lies beyond has led us through the cosmic microwave background, through the mathematics of eternal inflation, through the strange geometry of higher dimensions. But there remains one more territory we must explore. A realm where physics and philosophy merge into something altogether new. The question of why anything exists at all. This is the deepest question humans have ever asked. Not what is the universe made of, not how did it begin, not where does it end, but why is there something rather than nothing? For most of human history, this question was the province of religion and metaphysics. The universe existed because a creator willed it into being. Or the universe was eternal, without beginning or end, requiring no explanation for its existence. Or the question itself was somehow malformed, based on assumptions that did not hold at the deepest level of reality. But in recent decades, physicists have begun to address this question with the tools of science, and their answers, while far from complete, point toward possibilities that reshape our understanding of existence itself. The first possibility is that the universe came from nothing. Literally nothing, not empty space, which is something, not a quantum vacuum which seethes with virtual particles, but absolute nothingness, the complete absence of space, time, matter, energy, and physical law. This sounds impossible. How could something arise from nothing? Does not every effect require a cause? Does not existence itself demand an explanation? The physicist Lawrence Krauss has argued that quantum mechanics provides a mechanism for something to emerge from nothing. Quantum fluctuations can create particles from empty space. The total energy of the universe, including the negative gravitational potential energy, might sum to exactly zero. A universe could pop into existence without violating conservation of energy because there is no net energy to conserve. But critics point out that this is not really nothing. Empty space is something. The laws of quantum mechanics are something. The mathematical structures that describe these laws are something. To truly explain why anything exists, we would need to explain why there are physical laws at all, why mathematics describes reality, why there is any structure whatsoever rather than pure non-existence. Some philosophers argue that this question cannot be answered in principle. Any explanation of existence would itself be something that exists and therefore requires explanation. The chain of explanations leads either to infinite regress or to a brute fact that simply is, without further justification. But here is where modern physics offers an unexpected possibility. What if nothing is unstable? In quantum field theory, what we call empty space is not truly empty. It is a roiling sea of virtual particles, constantly appearing and disappearing, borrowing energy from the vacuum for brief moments before annihilating back into nothingness. The vacuum is not the absence of activity, but a specific state of quantum fields, a state with particular properties that determine what particles can exist and how they behave. What if absolute nothingness, true nothingness, has similar properties? What if the absence of everything is not a stable condition, but an inherently unstable state that inevitably gives rise to something? This is highly speculative. We have no way to study true nothingness, because any study would involve something, the observer, and the tools of observation. We cannot peer beyond existence to see what nothingness is like, but the mathematics of quantum mechanics suggests that instability might be a fundamental feature of reality. The vacuum decays, particles tunnel through barriers. States that seem stable turn out to be metastable, waiting to transition to something else. Perhaps existence itself is a quantum fluctuation from nothing. Perhaps the universe is what happens when nothing becomes unstable and gives rise to something. Perhaps being is the default state, and nothingness was never truly possible. This idea has profound implications for what lies beyond the edge of everything. If nothing is unstable, then something must exist. There is no alternative. The question of why there is something rather than nothing has an answer. There is something because nothing could not be, and if something must exist, then perhaps everything must exist. Perhaps every possible universe, every conceivable configuration of matter and energy, every logically consistent structure has reality. The multiverse would not be one possibility among many. It would be inevitable. This is the mathematical universe hypothesis proposed by physicist Max Tegmark. It suggests that mathematical structures do not merely describe reality. They are reality. Every consistent mathematical structure exists as a physical universe somewhere in the multiverse. In this view, our universe is one structure among infinitely many. Other universes embody other mathematical structures, other patterns of existence, other ways of being. The multiverse is the set of all possible worlds, and every possible world is actual from its own perspective. This is a staggering vision. It means that everything that can exist does exist. Every possible version of you, every possible history, every possible future is realized in some universe. The edge of everything is not a boundary, but an invitation. Beyond lies not nothing, but infinitely more somethings. Many scientists find this idea unacceptable. It seems unfalsifiable, more philosophy than physics. How could we ever test whether other mathematical structures exist as physical realities? How could we distinguish a universe where everything exists from a universe where only our cosmos exists? Tegmark argues that the hypothesis makes predictions. Our universe should be typical among universes that can contain observers. The physical constants we observe should be near the values that maximize the probability of observers emerging. The mathematical structure of our cosmos should be relatively simple, because simpler structures are more common in the space of all possible structures. These predictions are vague, difficult to test with precision, but they point in the right direction. Our universe does seem to have physical constants compatible with observers. Our cosmos is described by relatively simple equations. We might be exactly what we would expect to find if the mathematical universe hypothesis were true. But whether or not this specific hypothesis is correct, it illustrates something important about the question of what lies beyond. The answer may not be a place or a thing, but a principle, a reason why reality has the structure it does, a logic that governs existence itself. And this brings us to the final frontier of our exploration, the relationship between reality and information. We touched earlier on the holographic principle, the idea that the information content of any region of space can be encoded on its boundary. But the implications of this principle extend far beyond what we discussed. If the universe is fundamentally informational, then the question of what lies beyond takes on new meaning. Beyond might not be a location in space, but a level of description. Beyond might mean the deeper layer of reality from which our universe emerges. In this view, the physical world is not fundamental. What is fundamental is information, pattern, structure. The particles and forces we observe are manifestations of underlying information processing. Space and time themselves are emergent, arising from more basic relationships among bits of information. The physicist John Wheeler captured this idea in a famous phrase, "It from bit." Every particle, every field, every element of physical reality derives its existence from information. The universe is not made of matter. It is made of answers to yes or no questions. It is a vast computation, processing information according to rules that we call the laws of physics. If this is true, then asking what lies beyond the universe is like asking what lies beyond the program while you are inside the simulation. The answer is the computer running the simulation. The answer is the level of reality in which the computation takes place. Are we living in a simulation? This question, once confined to science fiction, is now taken seriously by some physicists and philosophers. The argument is straightforward. If civilizations can create simulated universes, and if such civilizations exist, then simulated universes vastly outnumber real ones. If you cannot tell whether you are in a simulation, then you should assign significant probability to being in one. The simulation hypothesis is disturbing for many reasons. It suggests that everything we know and love might be running on cosmic hardware that could be turned off at any moment. It implies that our reality might have creators, beings who design the simulation and who might be observing or manipulating it. It raises the question of what lies beyond the simulation, what reality the simulators themselves inhabit. But there is a sense in which the simulation hypothesis does not change anything fundamental. Even if we are simulated, our experiences are real experiences. Our lives have meaning to us. The universe we observe still demands explanation. The questions we ask still deserve answers, and the simulation hypothesis points toward a deeper truth. Reality has layers. What seems fundamental from one perspective might be emergent from another. The edge of everything might be the boundary between levels of description, the interface where one layer of reality gives way to something deeper. Perhaps there is no bottom. Perhaps reality extends downward as infinitely as it extends outward. Layers beneath layers beneath layers, each one giving rise to the one above, none of them truly fundamental. Or perhaps there is a bottom. Perhaps there is a level of reality that simply is, that requires no further explanation, that constitutes the bedrock of existence. This level might be mathematical or informational or something we cannot yet conceive, but it would be what lies beyond everything else. It would be the answer to the deepest question. We do not know, we may never know. The question of what lies beyond the edge of everything may exceed the limits of human understanding. We are finite beings, embedded in a particular universe, constrained by the cognitive architecture that evolution gave us. There may be truths we cannot grasp, realities we cannot imagine, answers we cannot comprehend. But we keep asking. That is our nature, that is our glory, and in the asking, we participate in something larger than ourselves. We join the conversation that the universe is having with itself. We add our voice to the cosmic inquiry that has been unfolding since the first conscious being looked up at the stars and wondered. What lies beyond? We have traveled far in our exploration. We have crossed billions of light years and billions of years. We have ventured into realms where space and time lose their familiar meanings. We have confronted ideas that stretch the limits of human imagination. Let us now gather what we have learned and consider what it means. The evidence suggests that our observable universe, the 93 billion light-year sphere we can access with our telescopes, is not all that exists. The mathematics of cosmic inflation implies that our cosmos is one bubble among countless others in an eternally inflating multiverse. The anomalies in the cosmic microwave background hint at influences from beyond our cosmic horizon. The fine-tuning of physical constants suggests that the values we observe might be selected from a vast ensemble of possibilities. Beyond the inflationary multiverse, even stranger possibilities await. Our universe might be a brain floating in a higher dimensional bulk, alongside other brains that constitute other universes. Our cosmos might be holographic, with all its information encoded on a distant boundary. Our reality might be a mathematical structure among infinitely many, each one as real as our own. These ideas are not proven. They are theoretical frameworks, extrapolations from known physics, attempts to make sense of a cosmos that exceeds our direct observation. But they are not arbitrary speculation. They emerge from our best theories of physics, from rigorous mathematical analysis, from the persistent attempt to understand the universe at its deepest level. And they converge on a remarkable conclusion. The edge of everything is not what it seems. We imagined a boundary, a wall, a place where reality simply stops. We pictured the universe as a finite container with an inside and an outside. We asked what lay beyond, expecting an answer in familiar terms: more space, more matter, more of the same. But the edge of everything might not be a place at all. It might be a transition between levels of reality, a shift from one kind of existence to another. A boundary not in space, but in the nature of being itself. Beyond our universe might lie other universes, but those universes might be beyond in the sense that they exist in different regions of an inflating multiverse, separated from us by expanding space that light can never cross. They are real but inaccessible. They exist, but not for us. Beyond our brain might lie other brains, but those brains might be beyond in the sense that they exist in extra dimensions we cannot perceive. They are millimeters away in the bulk, but those millimeters extend in directions perpendicular to everything we know. Beyond our mathematical structure might lie other structures, but those structures might be beyond in the sense that they embody different patterns of existence, different logical relationships, different forms of being that share nothing with our own. The edge of everything dissolves as we approach it. There is no wall, there is no boundary. There is only transition, transformation, transcendence. And perhaps this is the deepest lesson of our journey. The universe is not a thing but a process, not a place but a becoming, not a container but a flowering. What lies beyond the edge of everything is more of the same, but also infinitely different. More existence, but existence in forms we cannot imagine. More reality, but reality that exceeds our categories. We are not trapped inside a cosmic bubble. We are participants in a boundless unfolding. We are the universe exploring itself, consciousness probing the limits of being, existence reaching for its own edges, and finding that there are no edges, only more existence. This is not a conclusion, but an invitation. The edge of everything is not where inquiry ends, but where it truly begins. Every question we answer reveals deeper questions. Every mystery we solve opens onto greater mysteries. The horizon recedes as we advance, revealing landscapes we never suspected. And this is as it should be. A universe with a hard edge, a final boundary, a definitive answer would be a universe that could be fully known. It would be a universe that could be contained in a human mind, reduced to a set of equations, explained without remainder. Such a universe would be smaller than we are. It would be less mysterious than our own consciousness, less deep than our own longing, less infinite than our own imagination. The universe we actually inhabit is not like that. It is larger than we can measure, stranger than we can conceive, more mysterious than we can fathom. It exceeds us in every direction. It humbles us with its vastness and astounds us with its intricacy. And yet we are part of it. We are made of its matter, governed by its laws, embedded in its structure. We are the universe contemplating itself, the cosmos becoming conscious of its own existence, existence awakening to its own mystery. What lies beyond the edge of everything? We do not know, we may never know, but we will keep asking, we will keep exploring. We will keep reaching for the edge of everything, knowing that it will always recede before us, knowing that the journey has no end. Because this is what we are. This is what we do. This is what it means to be human. We are the universe's way of asking questions. And somewhere out there, beyond the edge of everything we know, the universe is waiting with answers we cannot yet imagine. The journey continues. If this exploration has changed how you see reality, there is always more to discover. The universe reveals its secrets reluctantly, one mystery at a time. But each mystery illuminates more than it conceals. Each question opens doors to chambers we never knew existed. Look up tonight at the stars. Know that you are looking at the past, at light that has traveled years or centuries or millennia to reach your eyes. Know that beyond what you can see lies more than you can imagine. Know that you are part of something vast and ancient and ongoing, something that extends beyond the edge of everything into realms of existence that no human has ever glimpsed. And know that the questions you ask, the wonder you feel, the curiosity that drives you to understand, these are not separate from the universe. They are the universe. They are the cosmos awakening, reaching for its own depths, seeking what lies beyond. You are not outside the mystery. You are the mystery contemplating itself. And somewhere out there, beyond the farthest galaxies, beyond the edge of the observable cosmos, beyond the boundaries of space and time themselves, something waits to be discovered. What is it? We do not know, but we will find out. The universe will not keep its secrets forever, and we are only beginning.